Recording in progress. good morning. How was your holiday week? Good morning, everyone. We weren't here on Monday because it was a holiday. So I hope you had a good holiday. It stayed cool. Gosh, it was warm, wasn't it? And I don't mean warm, I mean hot. How hot was it where you were? I think where I think it peaked out at about 116 degrees.
Well, my car's thermometer always reads higher than what my phone says, so clearly I have to use the car's temperature. So it was 124.
Oh my goodness. On your driveway?
Yeah. Pulled off to about 120 for the drive.
That's crazy. I mean, I was driving around yesterday and it said it was about 120, and I figured, well, that must be like some of the heat coming off the road.
Yeah, that's what I think.
And for those of you who are not familiar with Fahrenheit, that was about 46 degrees. Not the 120, the 116. So add about 2 degrees to that. So almost 50. That was a record, wasn't it? I mean, like, they said it was like an all-time record. Like, it had never, ever been that hot around here.
Yeah, I think Sacramento hit a record yesterday.
Crazy. Well, a little bit cooler today. Only 109, they said. And then maybe by Saturday, it'll dip below the hundreds. Maybe. And I saw someone posted, like back on Saturday, was it? Maybe Friday, when the temperature was still ramping up. Someone posted a meme of like the high temperatures around the area. It was like, Sacramento 105 and San Jose like 102, and I don't know what the other one was, like Stockton or something like that, 108, and then it said San Francisco 61. It said, San Francisco's having nothing of it. And then, what was it, on Monday, they said, it was like the hottest temperature it had ever been in San Francisco. And I said, what, was it like 73?
Well, I grew up down there. It would always get warm in September. Like right when we went back to school, we'd start having nice days.
Yeah, what did like Mark Twain say about San Francisco? It was like the coldest season he'd ever spent was summer in San Francisco.
The coldest winter I ever spent was a summer in San Francisco.
Yeah. Well, let's see. We're starting on arrays. Finally. Some of you have been looking forward to this. So now I'm going to assume that since you've taken the introductory programming course, you've already had a bit of an introduction to arrays. So your arrays might be something like arrays of integers or arrays of strings, and hopefully you did something with those arrays besides just store information in them. Maybe you sorted them, maybe you searched them for a particular value that you were looking for. But we're going to start out with kind of an introduction to C arrays. They're a little bit different than Java arrays, and we'll highlight the differences, the primary differences between them. So let's say in Java, you wanted to create a I got to do this. You wanted to create an array of 10 integers. How would you do that in Java? Well, you probably do something like int bracket bracket, and let's say the array is called nums. So nums equals new int bracket and then a 10 inside there. So that would tell Java to set aside 10 integers for an array. In C, it's a little bit different. It's actually a little bit simpler. You just go like this. You go int nums bracket 10 semicolon. That's it. So in Java, you have to create the variable, in most cases called nums, and its type is integer array. And then you have to create the array of 10 integers and then hook those two together. And in C, you just say, here's the type, it's integer. Here's the name, it's numbers. And then inside of the square brackets, you just tell it how many numbers to do. So here's some primary differences. In C, the array is a local variable. It will go out of scope when the function ends, or when what am I trying to say there? It has a local scope, right? So as soon as you leave the set of curly braces, it goes out of scope. So it will disappear when it goes out of scope. So with what we know right now, that means we can't create an array that's going to stick around. So we can't, so let me write this down. From what we know, sorry, I just turned my microphone volume down because I saw I was overloading things. Let me try this. From what we know now, we can't create an array in a function and have it exist once the function is done. In Java, you can do that. You can create an array in a method, and then another method can access that array. So in Java, it is allocated differently, allowing you to have an array that continues to exist outside the function or method that created it. Okay, so do you have any questions for me about that? Okay, so let's do some examples. How would you create an array of 20 doubles, and we'll call it ages? And how would you create an array of 50 blaps, and we'll call it a bloop? And finally, how would you create an array called an array of, let's say, 1,000 pixels, and we'll call it IMG. So here's three arrays we want to create. One is an array of 20 doubles, one is an array of 50 blaps, and one is an array of 1,000 pixels. How would you create each one of those? So go ahead and put those in the chat. I'm looking at some of the answers in the chat, and they look pretty good. Let me look at this here. There we go. All right, let's take a look at your solutions here. So for the first one, looks like pretty much everyone got that correct. You're going to put double, ages, and then in the brackets, 20. And then none of you fell for my sneaky trick here, which is to create an array out of something that's not an integer or a float or a string or so forth. So you did just fine on this. What did we do here? We went blap. No, we went, yeah, blap, bloop, 50. Now, you may be wondering, where did these things come from? What's a blap and what's a bloop? And where'd the 50 come from? Well, I was trying to get you to think there that if I just say create an array out of blaps, don't worry about what a blap is. It's just a type of something. And when you create an array, you put the type out in front, then the name of the array, and then how many elements. So at this point, don't worry about what those things are or where they came from. Just know that they exist, and you can create an array out of them. And you're right, blaps don't actually exist, but we could create a type. We could create a type called blap, and then create arrays out of it. And then finally, create an array of 1,000 pixels called image. So we have pixel, image, and then 1,000 inside the brackets. Okay, so the next thing would be assign the number 18 to element 0 of, we'll do ages, and copy element 0 into element 5 of ages. So two things to do here. Assign the number 18 to element 0 of ages and copy element 0 into element 5. So go ahead and do those. Well, I can't trip you guys up. So we got ages, bracket 0 equals 18. And for the copying, it's ages 5 equals ages 0. Perfect. For the ages array, what are the indices? What are the numbers associated with each one of the boxes? And we know that the numbering starts at 0, but what's the highest number?
The highest number is one less than the number you used when you created the array.
Yeah. So for the ages array, it'll be up to 19. For the bloop array, it'll be 49. And for the image array, it'll be indexed 0 to 999. Okay, so you got the general idea about how to create an array. Why don't we just see how we go about writing a program that would use these. So let's call this, I'm not feeling creative, let's do array.c. So let's just make it simple. Let's just prompt the user to type in 5 numbers, and then we'll just print them out. So we're going to store all the 5 numbers into an array. And for this example, we're not going to use a loop just yet. We're just going to use statements to read in the values, and then statements to print them out. So first thing we'll do is we'll create the array. Let's call it nums, and we'll put 5 elements in it. And then we'll just prompt the user to enter 5 numbers. We'll call this number 0. Prompt the user to enter number 0, and then we'll do just our regular scanf, but instead of putting in a single variable here, we're going to put in the name of the array, and then a bracket 0 to say that we want to put this into box number 0. And we still need to put the ampersand in front of it. And it'll probably be next week when we start explaining what that ampersand is doing there and why you would need to put it for some things and not for others. So the reason I'm putting these into separate statements instead of a loop of some sort is so that you can see the pattern that's emerging. And my experience has been that for some students who have taken the introductory programming course, you might have gotten loops kind of at the end of that course. And it may not be entirely intuitive to you just yet to know when to use a loop and when not to use a loop. And so I think from a teaching perspective, it's easier to see the use of a loop if you can see all the statements written out one at a time and then see that, oh, I'm repeating myself over and over again, and the only thing that's changing is this number, which could be the index to that loop. So in a few minutes, we'll condense this down into a loop, but for now, I just want you to see that they're all listed out separately. Okay, and then we're just going to print, we'll just print them all out. That'll be easy. So we'll just 5 numbers, all with spaces after them, and then we'll just list out nums 0, nums 1, nums 2, nums 3, nums 4, and that's it. We'll give that a save and we'll compile it. So enter number 0, I don't know, 5, 12, 0, 9, 4. There they are. Okay, so let's go back. And now we'll condense this down a bit and use a loop. So we'll use a loop to enter the numbers. And we could also change this portion down here to use a loop as well, although we won't be able to do it all in one line like I've got here. So when you're looking at a bunch of statements that are all pretty much similar except for 1 or 2 changing things, you should think, oh, that's probably a loop, especially if you can see in the pattern that there's a way to kind of calculate each one of those values. Here, we can see the numbers are just going up by 1 each time, so we can use a loop that just increments that number by 1 each time. So this would be a good use of a for loop. let's use I as our counter. You know, why do computer people use I for the variable? I mean, here's another thing that I think it's kind of like one of those unwritten guidelines, but I'll kind of spell it out here for you. When you're writing programs and another programmer encounters a variable with a particular name, he or she might look at that name and automatically infer what that variable is used for. So typically, variables with a single letter, especially if they're like I, J, or K, somewhere in the middle of that alphabet, those are pretty much always going to be used as loop counters. I think maybe I as being like index or something like that. But anyway, I, J, K, somewhere single letters in that range are probably going to be used as loop counters. If you see variables like X, Y, Z, W, those are probably going to be variables that are used kind of like as a place to store one value. Like you just need to input a single value, and you can't think of a name, you might just call it X, and then use that X later on, especially if you're only going to use it maybe once or twice. Like it's not going to be a variable that you use and then use it, you declare and then use it continuously through your program. X and Y obviously get used also for things like X, Y coordinates, so those are used there. And then anything else, any variable that has a longer name like age or persons or cars or computer, you know, anything like that is probably going to be a variable that gets used multiple times in the program and needs to have a good name so that you or anyone else looking at your program can kind of infer what its purpose is. But single variable, single letter names like I, J, K, probably going to be used as loop counters. So inside of the loop here, all you have to do is put the statements that repeat and then change the values, the numbers that are incrementing, and replace them with the value of our loop counter. And then I can take out all these. And then finally, for printing out, what I'm going to do is put it inside of a loop, and then I'll print out the number and a space, and then as the loop goes, it'll print out each one of the numbers with spaces after them. And then finally, after the loop is done, I'll print out the new line characters so that the cursor goes down to the next line. So we'll do another loop, a whole separate loop, because we want the loop to start over again. In the first loop is going to go to 1 to 5 and fill the array, and the second loop will go not 1 to 5, it goes 0 to 4 to fill the array, and then another loop is 0 to 4 to print out the array. You would not use something like a nested loop here, because a nested loop would cause the inner loop to run for every iteration of the outer loop. So the outer loop will run 5 times, and then the inner loop will run 5 times, for a total of 25 times. But I don't want to access these 25 times, I only want to access them a total of 10 times, right? 1 time through for filling the array, and then 1 time through for printing out the array. So a whole separate loop here. And then inside, we'll just have it print out a single number and a space. And then when the loop is completely finished, we'll print that new line character. And the reason why I'm putting it after the loop is because I only want that to be done once. Anything inside the loop, you'll put if you want it to repeat over and over again. And anything that only gets done once, you put outside the loop. All right, take a save on that, and then we'll compile it again. And we should see that it behaves pretty much the same as before. 5, 12, 0, 9, -4. Now all of these loops and arrays that I just wrote are all of size 5. The array is of size 5. The loop has 5 iterations. And so there's 1, 2, 3 places where I use the number 5. And if I change one of them, I'm going to have to change the other 2. If I change the size of the array, I should make the loop change as well. So that's 3 different places to change that number 5. A good way to handle this would be to put that number 5 away in some kind of variable so that I only have to change it once. So you could do something like int, and we'll call it like size equals 5 right here, and then just replace size 5 with the size. And then when you run the program, it still behaves as same as before. However, this value called size actually doesn't change throughout my program. I really shouldn't be changing that value. I shouldn't somewhere in the program, maybe accidentally increment the value of size, because now my array will be created with 5 elements, but my loops will go 6 times, and that'll cause a problem. So I should put that into a constant. There's 2 ways to do constants in C, and it kind of depends upon which textbook you're looking in, but kind of an older way to do it was to use a preprocessor directive called define. And this just says everywhere where it sees the word size, and by convention they're put in uppercase letters, everywhere it sees the word size, it's just going to replace it with the number 5. It's literally just going to do a search and replace. Okay, so the preprocessor is going to go through and look for the word size, and everywhere it sees it, just replace it with the number 5. So by the time the compiler gets your code, all of those size words have been replaced by the number 5, and the compiler has no idea that there was actually a different word there. All it sees is the number 5. The other way to do it would be to actually create a constant. And by convention, constants are given uppercase names so that they're easy to identify. So this one here says basically everywhere where you see the word size, just swap in the number 5 as well. But this is a preprocessor directive, which means by the time the compiler gets it, the word size no longer exists in your program and has been replaced by the number 5. And the second one is a compiler statement, and the compiler will go through and replace all the word sizes with the number 5. So right now there's pretty much no difference between the 2 of them. Both of them will cause basically that constant to go in there. If there's questions about it, I'll get into some of the subtle differences between the 2 of them. But I'd say for the now, go with either one, right? Either use defines or use these constant integers. They're both okay. So I'm going to go with the define for now. All right, so let's compile it and run it and see that, it still behaves exactly the same way. So what questions do you have for me at this point?
Yeah, in the text for defining, or I'm sorry, the data type they use for like array size, is size underscore t. Are you going to be talking about that today? And I don't. Why do they do that?
So it's supposed to look like this, right?
Yes.
Okay, that's actually not a variable name, it's a data type.
Right, right.
So,
I mean, as far as I could tell, it behaved like an int. I just wasn't sure what it was.
Actually, behind the scenes, I think that's a long. So the idea there is you as a programmer really shouldn't have to know what is the maximum size of an array that you could possibly make. And really, it's going to depend upon your processor architecture. For a 32-bit machine, the longest an array could be would be 4 billion entries, because that's the biggest number you can fit into a 32-bit quantity, 4 billion, give or take. On a 64-bit machine, it would be, 2 to the 64th would be the size, the maximum size of the array. Or basically the maximum length that anything could be in the computer would be 2 to the 64th, because that would be the maximum amount of memory that that particular processor could access. So size_t is a type that's been defined to be that 2 to the whatever value. And so on a 32-bit processor, that's basically going to be an int. And on a 64-bit processor, that's going to be a long. So by defining this size_t, it frees you up as a programmer from having to know, okay, what's the biggest length this thing could be on this processor, because I don't know what this is running on. Does that make sense?
It does.
Okay.
Thank you.
So if you go and look for examples on the internet of, how would you, let's say, what would be an example, like, define the size of a file that you're saving on the computer, it's probably going to use something like size_t, because that will be appropriate for the largest file that you could create on the file system, and you don't have to know what that is.
And also, isn't size t unsigned, so it keeps you from assigning a negative number to it?
Yeah, so it's an unsigned number. So I'm going to say, if you want to use that in your programs, that's fine. But again, this is introductory to C programming, and if you just want to use int, because we're not going to create files that big, we're not going to create arrays that are huge. So if you just want to replace this with int, I'd be fine with that. Okay. So the way you can create your own type, incidentally, is you use a statement called Typedef. And you put in, what is it? You put in the name of the existing type, like int, and then you put in the name of the alias you want to create for it. So this says, I've now created a type called blap, whose underlying type is int. So any type you create has to be created out of existing types. And the whole purpose here is just to give a new name for an existing type. Like I could do Typedef float to be length, or I could call it maybe centimeters. Okay, so now anytime I have a variable of type centimeters, it knows that really underlying that's just a float. So Typedef, all it does is just creates aliases for existing types. You take an existing type, and then you can give it an alias with a new name. So basically, anytime it encounters that new name, it just swaps in the existing type. So it sees CM there, and it just swaps in float. Which means that CM has all the same limitations of floats, has all the same uses for float. You can add them together, you can subtract them. I'm actually a little disappointed that that's all it does, is it just swaps in the name. It just creates an alias. What I wish that C did, and I'm getting on my little soapbox here, what I wish that C did was actually kind of create a new type with a new name. And yeah, it has an underlying representation, which is float, but otherwise they're considered to be different things. Because what I want to be able to do is go like Typedef float inches. Okay, so I have two types of measurements. I have centimeters and I have inches. Underlying are both just floats, right? Because you want to be able to do like 2.5 centimeters, and you want to be able to do 12.8 inches. That's fine, but I don't want to be able to do this. I don't want to be able to go centimeter length and inches width, and then do something like width equals length. Okay, this will compile just fine, and it will be no complaint whatsoever, because centimeter is just a float, and inches is just a float, so I can assign a float to a float. But what I wish the compiler did was flag this and say, hey, you gave those different names, and you're trying to assign them to each other. Width is actually inches, and length is actually centimeters. Now, of course, the compiler doesn't know that those are different units, right? But it should at least flag that and say, hey, it looks, although the underlying representations are just floats, you're trying to copy one type into another type, and you know, it should probably at least issue a warning to say this looks dodgy. But I believe this will just, it'll compile just fine, and there'll be no complaint whatsoever. Then the reason why I wish to give a warning is because obviously you wouldn't want to just assign centimeters into inches. It's not going to do the conversion for you because the compiler has no idea what these things actually are. It just knows they're different names. And you know, there was a fairly famous example of that, what, about 10, 15 years ago, when NASA, was it NASA or one of the space agencies was sending a probe to Mars, and the poor little thing hit Mars at, you know, way too fast a speed. Basically, it just crashed onto the surface. And the engineers finally traced the problem to the two teams that were working on the probe. One of them was working in metric units, and the other one was working in imperial units. Why? That's a different question. But nevertheless, when the part of the probe that, you know, activates the parachute needs to copy the information to the lander, it should have known that you can't just simply copy one set of units into the other set of units. There should have been like a flag to say, hey, whoa, you're trying to put metric units into an imperial variable. Well, of course, it doesn't know they're metric and imperial, but you're trying to put a value of one type into a value of a different type, and you can't do that. And it was just not caught because underlying the representations are just, they're just floats or just integers. And so I wish the C compiler at least flagged that. I wish this was at least a warning. But I believe it doesn't.
Whoops.
What's that?
I said whoops.
Yeah.
With the
About the crash lander, yeah. So 2 lessons learned there. One is, you know, make sure your types match up, and 2 is everyone should just be working a metric. Okay, so here's our little program. We just, you know, create a variable, create an array, and then input the numbers and then print them out. That's fine. But what would happen if I took out this size and I replace it with 100? Okay, so I'm gonna input 5 numbers into the array, but I'm gonna print out 100 of them. What do you think is gonna happen?
Wasn't expecting that to compile.
I think it'll just print out a bunch of garbage.
So someone didn't expect it to compile, but you can see it compiled just fine. And then someone said it's going to print out a bunch of garbage. What about third possibility, which is the program crashes?
Could do that.
Let's see what happens. Well, we got a bunch of garbage. We did get our 5, 12, 0, 9, negative 4. We did get those, but then we got a whole bunch of other stuff. So where did these numbers come from?
Can you explain the high frequency of zeros and ones?
Right here?
Yeah, there's just a lot of them in there for something that seems to be random garbage.
Well, the computer's memory is not really random. Remember,
Yeah.
What we're looking at here is basically vestiges and leftover pieces from programs that ran before. And zeros actually do happen quite a lot in programming. Like, they're sitting here as variable initializations, and zeros can be, in part because we're printing these out as integers, but some of those values there could be 64-bit memory locations. So we're printing them out as 32-bit numbers, but what was actually stored there was a 64-bit number. And part of that number might have been 0 if the addresses were like in lower memory. So we might see some zeros there because we print out one section of it as 32 bits and see a random number, and then the other section is just zeros because what was actually stored there was a 64-bit address, but most of it was zeros. I'll bet you if we run the program again, we'll get a different set of garbage. We do. See up here, there were a lot of negative numbers. Down here, not so much. What if we change this to like 10,000?
You might wind up crashing. You might get a segmentation fault.
So we got a lot of garbage values. There's a lot of zeros in there. But you're right, it did actually just crash my program. And you know what? I'm curious to see how high did it get before it crashed. So I'm going to print out the value of I and the value of num's I, and we'll see what happens.
Do I see a new file that has been created after that?
Yes. This one right here. I'll tell you about that in a sec. Okay, so it looks like this loop only got up to 1,238 before it just completely died, even though my loop was going up to 10,000. Okay, so we've got kind of like a lot of strange new things that just happened here. One is the compiler didn't complain when we told it we were going to just access too many elements of the array. I think in Java, this might actually not compile. The compiler might realize, oh, your loop is going from 0 to 10,000, and you're plugging that into the name of an array that only goes up to 5. I know that's going to be a problem, so it'll flag it. But C just lets it go. No complaint. The other is we get garbage values, and I think we probably know why we're doing that. But also, we didn't get any complaint at all when we initially ran off the end of the array with 100 there. It just printed out garbage values. And the third thing is, what is this segmentation fault and core dump thing, and why did it only get up to 1,238 before it died when it didn't get up to 10,000 or even anywhere close to 10,000? So there's a bunch of kind of weird things going on there.
If we run it again, will it fail on the same spot
Oh, that's a good question.
at 1238?
Nope. This time it died at 741. So it all goes back to this picture of memory that I laid out, what was it, last week? We have the text segment and the data segment. Free memory, and the stack segment. So in which of those 4 segments does this array that we created actually live in? Is it here in the stack, here in the free memory, here in the data, or here in the text? Now, while you're thinking
The
about that,
array's in the stack
why is it in the stack?
because it's a local variable.
Yeah, it's a local variable. So sitting here, somewhere in this stack, is this array called nums. So we told it, set aside 5 boxes, each of which can hold an integer. Integers are 32 bits or 4 bytes. So that means we set aside a total of 20 bytes for that array. But then our program says, go from 0 to 10,000. And so the program just happily starts reading through the array, and it walks right off the end of the array and keeps going. Although, the array is not arranged actually horizontally, it's arranged vertically. So it starts walking through the array and walks off the end of our stack segment. And as soon as that happens, as soon as your program tries to access memory that's not in one of these 3 allocated segments, so if it's somewhere here in this free memory, then the program is immediately terminated. That's a no-no. You shouldn't be looking in memory that you don't have access to. So the program just simply went right off the end of the array and kept going until it finally walked off the end of the stack segment. So that caused the program to crash. But why was it allowed to walk off the end of the array in the first place? Well, C doesn't prevent that, as you've seen. C does not prevent you from accessing elements of the array that don't exist. I mean, if you go way off the end of the array, then that's not C stopping you, that's the operating system and the processor stopping you. But the language itself does not prevent you from just walking off the end of the array. And what that also means is that C does not keep track of the length of the array. So once you've created the array with 5 elements in it, you cannot ask the array, how big are you? Now in C, you can, in Java, you can do that. You can use that length attribute to find out how long that array is. But C does not keep track of that information for you. You create the array, it sets aside the memory, and then it says, go for it. And it assumes that you, the programmer, are keeping track of that information yourself. You see, in our program, we're keeping track of it inside of this size constant. So the compiler or the runtime is not itself also keeping track of that. It assumes that you've kept track of it yourself. So it's up to you to make sure that you use the appropriate indexes in the array. It will not prevent you from walking off the end of the array. So that's probably one of the primary differences between C and Java, is that Java does keep track of the length of the array and C does not keep track of that. Java will stop you. It will not let you walk off the end of the array. C will just gladly let you go. Also, you don't have to, what am I trying to do here? Let's try something. Let's try a little experiment here. So let's put 100,000. Let's say 100 here again. So we're going to walk off the end of the array. But
I think you're on the wrong screen.
Sorry.
Yeah.
Here we go. So you didn't see what I wrote over here. I wrote these 2 lines. So C doesn't prevent you from accessing elements of the array that don't exist, and C does not keep track of the length of the array for you. Okay, so let's try this. Let's print out 100 elements of the array, but let's print it out as characters. Okay, I think this is not going to compile as it is. Oh, it did. Huh, look at that. So we can access an array as though it was a completely different thing. So again, C here is not saying, hey, whoa, this is an array of integers. You're printing out as characters. It just goes, oh, okay. Whatever you say, boss. You're in charge.
So the integer 3 translated to J. Am I seeing that? Is it pulling a value from memory?
No,
and
no.
saying that
These characters here, this 5, 12,
blank.
3, 9, 12, these are all these blanks up here, right?
I see.
Because the ASCII values for like 5 and 12, those are all like non-printable characters.
Mm-hmm.
They're called control codes, and so they would just appear as just blanks on the screen here. So these are the like those garbage values up here. Okay, so let's talk a little bit about how arrays are actually stored in memory. So if I create a 5-element array, it sets aside 5 boxes, but first it needs to calculate how many bytes to set aside. So we have int equals 32 bits, which means 4 bytes. So that gives us a total of 20 bytes here. 4 for each box, in a total of 5 boxes. And arrays are laid out in contiguous memory. So you got the first element, element number 0, then element number 1, then 2, then 3, then 4. And they're laid out in increasing addresses in memory. Let's assume the starting address is 5,000. Well, so what's the address? Where does box number 1 live? So if this point right here is 5,000, what is this one?
5004.
Good, 5004. Right, because each box is 4 bytes long. So if box number 0 lives at 5,000, the next one would be at 4 bytes later, which is 5004. What's the address of, let's say, box number 3?
$5,012. Unless I'm bad at math. Okay.
I think you're correct. So what's the address of box X? Whatever X happens to be.
$5,000 plus X times 4.
Good. So where did this 4 come from?
That's the size of an int in bytes.
Mm-hmm. And in C, you can literally write size of, and in parentheses, int. That's an actual function that is in the C language, and it returns the size of the type that you passed in. So we could do like size of char, and it would say 1. We could do size of double, and it probably says 8. Size of float, it says 4. Size of long, it says 8. So it tells you how big a certain type is. And so this is the calculation it does. Every time it wants to access the element of an array, it just takes the base address and adds the index times the size of the underlying type. And so that's the same calculation no matter what kind of array it is, whether it's a character array or a float array or a double array. It does essentially the same calculation. It takes the base address of the array and adds to it the index times the size of the underlying type. And so that's why it's able to walk off the end of an array. It just simply does that calculation. It just says, okay, you want to access element number 100. I'll just take the base address of the array and add to it the index, which is 100, times the size of the type, which is 4, and then that's the memory address it looks at. And since C doesn't keep track of how big the array is, it has no idea that it's accessing an element of memory or an element of memory that isn't part of the array. So how are we doing there? Whew, it's a lot of stuff, right? But I mean, it's a little strange. It's a little strange to think that C arrays seem to be a little bit easier to declare, but they come with like all these downsides. They come with things like you can walk off the end of the array, and the array, the length is not kept track of for you. So all these things you're kind of used to as both kind of benefits you get and protections against malevolent programming that you get in Java, you don't get in C. And you know, part of that has to do with the history of C. C has been around a very long time, since the early 1970s, I think. And so back then, of course, computers were slower and had less memory. And so it was chosen as a trade-off not to keep track of the length of the array, because that was an extra little piece of information that you had to keep around. And really, if the programmer is doing a good job, you shouldn't need to keep track of that anyway. The programmer is probably already keeping track of that. And why doesn't it protect against walking off the end of the array? Well, again, it has to do with the computers being a lot slower back then and having to check every time you access the array to check to see if the index is within bounds would slow things down. And again, if the programmer is doing his or her job, that wouldn't happen in the first place, because you'd be, since you're keeping track of the length of the array yourself, you wouldn't let it go beyond the end of the array. But it didn't take long, before, you know, 1980s or so, before people who didn't have the best interests of the users at heart figured out that they could use this as a way to attack programs and get access to parts of the program they weren't allowed to. And walking off the end of an array, which is sometimes called a buffer overrun, is a very common way to break a program, particularly ones that were written in C, because they don't check the array bounds. And so if the program is written in C and you do something like prompt the user to enter their name, well, you have to put that name in a string that you have pre-declared. And if you don't know ahead of time how many characters that user is going to type in, you're kind of up a creek. So you might set aside, let's say, 50 characters for their name, but what if they type in 100 characters? Well, that input routine is just simply going to go off the end of the array and keep putting characters into memory. And then what are you overwriting? You're potentially overwriting other variables. And maybe those other variables control critical aspects of the program. Maybe one of those variables contains information about whether or not you're a privileged user and can maybe alter records in a database. Privileged users can, regular users can't. Well, if you could overwrite that variable about whether you're privileged or not, you could break the program and get access to data you're not supposed to get access to, or be able to alter data you're not supposed to access. Alter data you're not supposed to be able to alter. So buffer overruns are a very common way to break C programs, particularly if the programmer has not been quite diligent about making sure the user input doesn't go beyond the end of the array. There's really kind of no way, given what you know now, to prevent that, because we're using input routines that don't check the length of the input and don't check the array that it's going into. Now, there are ways around that. You can use library functions that other people have written to do things like get input from the user and stop reading at a certain number of characters, or maybe create a string that grows as the user inputs values into it so that you don't ever overrun the array. It just makes the array longer and longer. There's some tricks you can do to do that. But then you got other problems, like if you basically allow unlimited lengths, then you can fill up the program's memory. Just type in so much data that you fill up every byte of the computer. And then what happens? Okay. Do you have any questions for me at this point? We're going to switch gears a little bit.
Yeah.
Yeah.
Something else that I saw in the text that I was surprised by. We have to define the length of the array. Mm-hmm. And I didn't see a way for the array to grow over time, like if we needed to add more to it.
No, that's the same problem in Java. Once you create an array of this style, you can't change the size. So same thing in C. Now, a moment ago, I said you create an array that grows, and so you have to do a different kind of array. So in Java, you would use something called array list, or something similar like that, which is really just a wrapper around regular arrays, but has this added benefit of allowing it to grow. And the way that Java does it is, once you create your array that's of a fixed size, and then you want it to grow, you actually create a new array that's bigger, and then copy all the values over into the new one and throw the old one away.
Oh, that's cool.
So you can kind of do the same thing in C, you just can't do it like with the standard arrays.
I see.
So right now, I'm just trying to leverage, hopefully, existing knowledge from your Java days, and then show you the equivalent in C. And then, once you're familiar with that, we can start showing you, okay, what's the C way that would allow arrays to expand. Okay, so I'm going to talk now about how would you go about passing arrays into functions. And I said earlier that one of the limitations of C was that you couldn't create an array in one function and have it exist in another function. In particular, you can't, let's say, have a function create the array and then get that array back from that function. But you can create an array in a function and then pass the array to another function. Okay, there's a subtle difference there. One of them is the array is being created in one function, and then that function disappears. And then at that point, that array ceases to exist as well. But as long as the array is still on the stack, then you can still get access to it. So remember that visualizer was showing the stack frames piling up. As long as the stack frame for another function still exists, then that array still exists, and you can get access to it. So we have our program here, which gets input from the user and then prints it out. I want to take this portion of the program and put it into a function. And I can do that as long as I create the array in main and then pass that array into the input function. And then I also want to do the same thing for the printing part. I want to take the array and print out the values and make that its own function as well. Let's actually start there. So let's put everything back the way it was. And let's create a function called, I'm going to put it up here. Let's call it print array. And we'll get in a moment into what you have to put inside the parentheses because we're going to pass the array in. But let's just copy and paste the code that we had here and put it up here. Okay, so I just took the code that was down here, and now here I'm just going to say print array, and I'm going to pass in the name of the array that I want to print out, which in this case is nums. Okay, so I'm going to call print array, and we're going to pass in the name of the array that I want to print out. This would allow me to now print out any array. So if I got an array called ages, I could print that one out. If I got an array called number of pets, I can print that one out. I only need one function to be able to do all these different things. Okay, so up here, we need to pass in this array. So what is going to be the type of the array? Well, the way you pass it in looks a lot like the way you declare it in the first place. Let's just call it ARR, right? It's just a generic array. So let's go int ARR, and then just put the 2 square brackets. And this just says that we're passing in to this function an integer array called ARR. So notice it doesn't contain the number of elements because this function does not need to know how many elements in the array are in the array. In fact, it doesn't know. So it's just using this size constant as a way to get that information. Okay, let's just make sure that works. So let's save it. Compiles fine. And then we'll put in our numbers. And then element number 0 has value 51. It didn't print out as nicely as I wanted it. Here, I'm going to put the spaces in a different place, and I think that'll make it clearer. There, that's better. So element number 0 has value 5, element number 1 has value 6, 2 has 9, 3 has 12, and 4 has 3. Okay, so that's how you pass an array into a function. You just basically give it what the declaration looks like, right here, but without the number inside of the brackets. Okay, and then we'll do the same thing for the input. We'll pass in the array, and then the job of input array will be to go and fill in the values. And again, we're using this size that comes from the constant. And it works. All right, So there's one last thing about passing an array into a function. And that gets back to this fact that C does not keep track of the length of the array for you. So our input and print functions here have to rely on this constant that we've set aside for the length of the array. But what if we passed in the array nums here, whose size is known to be 5, and we had another array called ages, and let's say we'll put 10 elements into that, and maybe we'll create a constant for that as well. So when we call print array or input array, it's still going to rely on that size, whose value is 5. But the ages array, is of size 10. So how does input array get that information about how big the array is? And the way it's written currently, it doesn't. It doesn't have that information. It assumes that it's just a value of 5. So the way to do that, and this is the colloquial, idiomatic way that C does it, is unless you know absolutely for sure how big that array is, you should pass that in as an additional parameter. So if you're writing a function that just works on arrays in a generic fashion and it doesn't assume the length, it doesn't need to assume the length of the array, or can't assume the length of the array, then you need to pass that in as a second parameter. So you're going to pass in the array itself and its length. And so that's how I would like you to write your programs that are being passed in arrays. You're going to pass in 2 parameters, the array itself and its length. So we'll do the same thing for both here. And then replace this constant with that parameter you're passing in. And then down here where you call the functions, you need to pass in its length. And now the functions know how long that array is. Seems like a little extra work, right? You're having to pass in 2 things, the name of the array and its length. But the reality is, even in Java, it still does the same thing. Since arrays do keep track of their own length, they actually do have a separate variable set aside for that length. It just doesn't get passed in as an explicit parameter, but the information does go along with it.
Is there an operation like a size dot or a length dot array name that will automatically feed us that value?
Kind of. Depends. I wouldn't rely on it. And I think the textbook touches on this. So it depends upon how the array was allocated. So you could do something like size of nums, and it will tell you. But it will tell you the number of bytes. So in this case, it will return 20 to you. So you'd then have to divide that by the size of the int to get the actual number of elements. So, maybe that's useful for you, kind of, but if the array had been declared a different style, and there's probably like 3 different ways to declare arrays in C. I've only shown you one of them. In this declaration here, you're telling it, okay, the number of elements in nums is size, and then it knows how much memory to set aside. There's also a way in C to declare an array to say like, hey, I'm going to have an array here. I don't know the size yet, but I'll tell you later. And in that case, when you ask for the size of nums, it doesn't tell you 20, it tells you the number of bytes that the address takes up. In this case, 8, because it's a 64-bit machine. And it will always be 8, right, no matter how big the array is. And so that's not useful. It tells you how big your address is. It doesn't tell you how many elements are in the array. It's kind of like, could I tell you how many people are living in a home by its phone number or address, like literally the street address? No, you can't, right? Right? Every time you say like, how big is the address? It just says, oh, it's 4 digits long. It has nothing to do with the number of people who are in that house. Okay, so there is this size of, but it will tell you the number of bytes. And so you might be able to maybe, get the length of the array, but it's not reliable because you could do the size of something else, some other array, and it might just say 8. So that's why I would say don't rely on that at all, and just assume that the length of the array is not stored with the array and it's stored somewhere else. All right?
Yep.
But no, there's no attribute like length or size that you can use. Not at all. Again, that was a reason why Java put that in there, because that was like such a common thing to do. And like one of the biggest complaints about C was the fact that you had to keep track of that yourself. Why can't the arrays keep track of that? I mean, if we're going to be keeping track of it ourselves, why don't the arrays keep track of it and use the same amount of memory? So that's why Java keeps track and C doesn't. Of course, Java came around in the 90s when computers were faster and more memory, and you could afford to use an extra 4 or 8 bytes to hold that information.
So we have, there's different versions of C. Like, how often does C get updated?
Not very often.
Yeah. I want to, what, this book says C11. Was it the last time it was updated was 11
Yes.
years ago?
Yeah.
Oof.
So what are the kind of overarching philosophies behind C is, since it's been around so long, programmers have come to rely on it as a stable workhorse that just always does what it's supposed to do. Nothing more, nothing less. And so although there are new new features being added to other languages all the time, the standards body that defines what C is have decided we're going to change the language as little as possible so that people can rely on it as not changing a lot. The problem with a language like Python is it changes constantly, and to the detriment of existing programs. When they switched from Python 2 to Python 3, a lot of old Python 2 programs just refused to work because the syntax had changed so much in those versions. What was allowed, or I should say, what meant one thing in Python 2 meant something different in Python 3 because they decided to change the syntax. And so a lot of people stuck with Python 2 for years and years because they didn't want to change the programs to version 3. Because maybe they had gone through a huge validate procedure to make sure the program worked correctly, and now you're asking us to change the underlying syntax? I mean, now we got to go through all that validation all over again. We might as well just stay with Python 2.
Yeah, a syntax change, that's wild to me. Like,
Yeah.
you know, adding additional features without changing the syntax seems less crazy, but
In some cases, Python 3 was fixing stuff that was broken in Python 2. I mean, when Python 2 came out with, you know, feature X, they kind of glommed it on to the existing syntax, and people after a while said, that's crazy. Why are you doing it that way? You know, when everyone else does it using these other symbols. Why don't you, you know, get with the program and do it the way everyone else expects you to do it? So finally in Python 3 they said, okay, we'll do that, but it means that your existing programs will break. So Java has tried as much as possible to keep the syntax, I mean, to add on to the syntax without breaking the old stuff. But I think in one of the more recent versions of Java, they finally said, okay, it's about time that feature X is just not going to work anymore the way you expect it. You're going to have to change it. So yeah, C11 is the most recent, although I think there's a new version coming out imminently, and I don't remember what the number is. It's not like 23. The problem is that that version of C was proposed a few years ago, and then it takes a few years for the standards body to actually approve it. So the number that I think there's going to come out is like C20 or 21 or something like that, even though it may actually be approved in 2023. And you can go find out. You can go find out what are the changes. Changes in C20? 21?
2x.
Yeah, they call it 2x because they don't know what year it's going to actually.
Yeah, that's what I'm saying.
They don't know actually what year it's going to be called.
And I guess there's a C17.
Oh yeah, look at that. So finally getting rid of old style function definitions. Like, no one uses these anymore. You can now separate digits in a number with apostrophes. They didn't put in here the one thing I was really looking for, and that was function overloading. Having two functions with the same name but different parameters. Every other major language, Python, Java, C++, allows function overloading, but C does not allow function overloading. And I think there was a proposal in this 2020 or 2021 version to finally do function overloading, and it looks like it didn't make the cut.
Wait, does that mean that when you have the two functions with the same name, that the newest one would overwrite the old one?
No, you'll get an error. It says you can't have two functions with the same name.
Oh, okay.
I can see the hesitancy to change in the length of this changelog. There's not a lot.
Not a lot, yeah. Whereas, you know, this would be like the weekly changes in Java or Python. And a lot of those other languages, especially in Python, a lot of these changes are like fixed bug, fixed bug, fixed bug, because it just changes so much, and bugs creep in all the time. This K&R function definitions, finally getting rid of that. In the old, so K&R is the very first version of C, the Kernahan and Ritchie version. And in that one, you could declare a function kind of like this. You could say foo x. And it would know this is a function definition because it contains the name of a function. It's followed by two sets of parentheses. And so you can, and it's not followed by a semicolon, and it is followed by braces. So the compiler looks at this and goes, oh, that's a function definition and not a function call. But what's the return type? Well, if you don't specify the return type, it's assumed to be int. And if you don't specify the type of the parameter, it's assumed to be int. So this foo x is equivalent to int foo int x. But what if x is not an int? Well, then what you do is you go like character x down here. So notice that in between the function declaration and the opening brace is a type declaration, and that tells it what the type of x is. You know, and what if this returns something other than an int? What if it returns a character? Well, then you have to put it in. Right? But in K&R, there was a lot of implicit type declarations, assumed to be int unless told otherwise. So I'm kind of glad to see that gone, because that was just kind of crazy. Not keeping up with current language trends, which is to put the type, then the function name, and then the types of all the parameters. Okay, where were we with this array function? Oh, oh, it's already 10:54, so that's usually when we would take a little break, because people need to get a drink of water or visit the restroom. So I think I'm going to do that. I need a drink of water. So what we're going to do is we're going to take this program that we wrote and we're going to drop it into that stack visualizer and see what's actually going on here. And then hopefully by then we will have gotten enough about C functions that we could start tackling the first couple of programs that are on this week's list. So why don't we take a little 5-minute break. We'll come back around 11 o'clock. And we'll talk about the remaining stuff, and then we'll call it a day. Someone on YouTube here was asking about a project I was supposed to be working on over the summer. A little bit of backstory there. I know someone who has muscular dystrophy, and his muscles have deteriorated to the point where he can really only just move the fingertips of his hands, and he can move his head a little bit, and that's about it. And so he wanted to play video games. He was an avid gamer when he had more motion in his hands, and now he's unable to play video games because he can't move the controllers with his thumbs. And so I thought I would at least try to make a controller that could be moved with very, very little strength. And so at the time, I think I have that prototype here. Oh yeah, here it is. So I took this Wii nunchuck that has this on it, and I hooked it up to a little microcontroller right here. And what this does is it takes the binary, bits that are coming off of this digital controller and it basically translates it into the binary bits that a what am I trying to say? Would be used for like, it's basically translating it from, this kind of joystick to a different kind of joystick, or a mouse, or it's doing mouse translation. So it's turning it into a mouse, basically. But the problem there was, once I showed this to him, he said, I can't even move this with my thumb, right? Even if I just have, my fingertips here, I can't put enough strength on it to move it. So, although this prototype was successful as it worked as designed, the problem was design was not good because this is just too difficult to move. So then I thought about, let me go reach into another bin over here. Is this the bin? I thought it was. This is not the bin I thought it was. Right? Oh, yeah, it is. So then I thought about, I was inspired by the IBM laptop or ThinkPad keyboards. And if you're familiar with those are the keyboards that have this unique feature of having a little red nub in the middle of the keyboard that you could put your finger on and move the mouse around with that. And some people love that because you really don't have to move your hand very far to get access to this little nub. And the way that nub works is it's basically a force sensor that can detect whether you're pushing on the nub, forward or backwards or left or right or any angle thereof. And so then I said about, well, how do I obtain one of those keyboards? And you can order replacement keyboards on Amazon for like $10 or so. And so I stripped out that keyboard and I pulled out the little nub. This is it right here. And all this is two variable force resistors. And so one measures the X direction and one measures the Y direction. The problem with these sensors is that, they basically don't move. Underneath the red cap is just a little, what'd you call this? A little metal protrusion right here, right? And basically it doesn't move. It just it measures the force that you're pushing on it. It doesn't actually move. And so my idea was to maybe glue or attach some kind of longer stick to this. Trying to use something I could use as a mock-up, but think about, here we could probably use something like this. Right, so basically I could attach a longer pole to this, and then if you're able to use basically no strength at all, you could push this pole to one side or the other, and that would exert a force on that little protrusion. I'd be able to measure it. So that was something I set out doing. The problem there is that when you're pushing on that little nub with your finger, you're probably not thinking about it, but you're actually exerting a fair amount of force on this, and you can measure it easily. This is exerting almost no force at all on that little metal thing there. And so the amount of deflection you're getting is extremely small, and it's very hard to measure that in a reliable way. Nevertheless, I'm still toying with this idea of maybe having this thing not be a metal thing, but actually be like a plastic rod that has a little bit of flex to it, and that might exert a slightly bigger force on this. And so he would basically be able to use his finger to just move it a little bit. So the Lord Melbury is mentioning the Hall effect. So a Hall effect is basically a sensor that can measure the presence of a magnet, and then you could put magnets on this. That's actually how some of the low force controllers work, is with Hall effect sensors. That's how the control on his wheelchair works. And so he can push that controller forward with his thumb, and then it'll measure him going forward, but there's essentially no resistance at all to that. The problem there is that it's not a continuous measurement. It's just on or off. Either the magnet is either there or not there. And that's not great for like a game where you need to be able to have a finer control over your motion in the game. Nevertheless, I'm not giving up on this idea, because this is cheap, right? These are, strip out the keyboard and all you're left with is this little thing. And then I also thought, well, since he can move his head, can we do something with like a motion sensor? Could he maybe put on a cap, and then there'll be a motion sensor on the brim of the cap. So if you want to turn left, he would just turn his head left, turn right, go forward, go back, like that sort of thing. And I thought that was actually a pretty good solution, except for, and this is the tough part, except for the calibration issue. So like you put on this cap, how does the cap know that you're holding your head level and not like, tilted to one side or the other? And so you'd have to have some kind of calibration phase where you push a button on a controller or something and say like, okay, this is what I consider to be centered, right? And the problem is that when he sits in his wheelchair, he doesn't sit upright. He kind of like leans back a little bit. And so you would have to basically say, okay, this is considered to be centered. And then when he turns his head, right, it's not turning on a horizontal plane, it's actually turning on a slanted plane. So we'd have to say like, okay, this is considered left, this is considered right, even though it's going, actually, but it's not considered up, right? This is up, going on this plane. So there's that issue. And then the final issue is like, what if he's playing and a fly comes and he goes like this, right? What happens then? So maybe he needs another button that he can press to say like, temporarily ignore this input. Or maybe the controller could be smart enough to know that if you see that happen, just ignore that, right? Ignore any wild deflections. So, like I said, I didn't make as much progress on that this summer as I had hoped. But there is actually a company called Evil Controllers, and that's kind of like their job, is to make controllers for people with limited mobility. And so they can take an existing controller and they could like replace the springs inside of them with low resistance springs. They also make custom controllers, so you got this little like basically a little thumb controller that attaches to an existing controller, again with low resistance springs inside of them. But this would be something where you could take this piece and you could maybe adhere it to your wheelchair arms, so that you could, if you couldn't move your arms, at least the controller could be right there. Or you could put, so if you can't move your arms, you can't bring your arms closer together, at least you could have the controllers separated now by a couple of feet. So you can write to them and you can say, here's my issue. here's what I need, and then they, if you, I guess, pay them, they will design and build a controller for you. So I'm kind of in contact with them about maybe that would be the thing to do, is just have them either leverage one of their existing products or create something brand new for him. So that's where that project is right now. I guess the answer is stalled, but hoping to get something going. Oh, one more thing was Hall effect sensor with a magnet on your finger. That might not be a bad idea if you're wearing some kind of like little fingertip thing that has a magnet on it, and then you could remember he can only dangle his hands, right? So then kind of sensor that he's able to move that around in. I had initially thought of putting a motion sensor on his finger to do this kind of the same thing. I don't know. I'll have to give that some consideration. Can I do that in 2 dimensions, right? Not just left, right, but also back and forth. And does the orientation of the magnet change any of that? So although I'd be able to detect certainly like one direction or the other, what if I move it this way? Does the north-south orientation of the magnet affect how that Hall sensor works? Those are just like, they're not necessarily stumbling blocks, are just like questions that come up, like, is this feasible? I think it would be. So it could be something to take a look at. Okay, I'm going to take this program and we're going to drop that into that Python tutor. Although we're not doing Python, we're doing C. And one of the limitations of this visualizer is it can't actually do input from the keyboard. So we can't actually prompt the user to enter a number and then have them type in a number. What we have to do is replace this code with just something that'll just simply assign the values. So I'm just going to drop out this loop, pull out this loop, and just go ARR 0 equals 5, ARR 1 equals 12, ARR 2 equals, let's put 0 in there, 3 is 9, and ARR 4 is like -5. Okay, and I'm also going to take out this ages stuff. We don't need that. Okay, I think that looks pretty good. Let's start the program. So when it starts out, of course, the array is filled with garbage values, but we'll click on Next. And then when I click on Next again, we're going to see this red arrow jump up to Input Array, and it's going to start walking its way through these 5 statements. Okay, so here we are in Input Array. We've got 2 variables, one called ARR and one called length. Before the array, before the function actually starts, of course, these 2 variables have no values, but let's see what happens when we click on Next. So we can see that length now has the value 5. That's what we'd expect because we were passing in the value of size, which is 5. But also ARR here does not contain a copy of the array. Instead, it contains what's called a pointer to the existing array. So I said earlier that as long as that array exists in another stack frame, you can access it. And so here, this array variable is accessing the nums array inside of main. So when we pass in the array right here, we're not passing in a copy of the array. We're passing in what some people would call a reference to the array or a pointer of the array. What we're actually passing in is the address of where that array lives in memory. Let's click on next a few times, and you can see it start to fill in that array with values. So although input array is doing the work, the effects of it are appearing inside of the main array. Okay, and now input array is done, and we go back to main, and the array has been filled in. So let's go into print array, and again, print array is going to get the address of where that array lives in memory, and it's going to start printing out the values. Looks like I can't quite get the next button down here and the output on the same screen at the same time. So we're just going to have to click through a few more times. Okay, now it's done. Here's our output. And then we jump back to main, and that print array stack frame disappears, but main still exists, and so the array still exists, and then our program is done. Okay, I'm going to show you one more example. Let's input the array and print out the array, and then I'm also going to have a function called double array, and then we'll print it out again. And the purpose of this function is to take all the elements of the array and double them. So 5 becomes 10, 12 becomes 24, and so forth. Now, why am I declaring these functions to be a void? Why are they returning nothing instead of like int array? Let me know, why am I putting void here in front of these?
Isn't it because you're referencing the array and not actually using copies?
Yeah. So these functions here are accessing the array directly. They're not returning a copy of the array. So they're declared to be void because they're not actually calculating something and then returning that value back to the caller. They're just accessing it directly.
If we did something like instead of void used int and then a return 0 at the end, would it all still work?
Yeah.
Or is the void necessary?
No, the void is here but simply because there's nothing in the program that returns a value. But if we wanted to return a value, we could, and the array would still behave as.
Okay.
Why don't we go ahead and just do that there? So just for anyone watching, just be sure you know that this int here is not technically necessary, but we're exploring this little question that was that Sean had. Okay, so this one here, I'm going to loop through the array, and I'm going to say array I is equal to array I times 2. So let's go back over here, and I'm just going to drop that code in. Okay, so let's get started with this. So click on next a few times. It's going to go into input array and fill that array in with those values. And then it's going to call print array. So it's building up the output. And then it's done with that. And now we're going to call double array. So we get a new stack frame. And then that array variable points to the nums array inside of main. And now as we loop through this, you're going to see those values getting replaced. And then finally, the stack frame disappears, and the array is left with all the numbers doubled. And notice that, oh, you know what? I forgot to put in that int x equals. All right, let's just fast forward here. We'll zip through this program until we get to double. Oh, I forgot to, oh my goodness, I forgot to put in the return 0 that you wanted. Okay, here we are instead of double array. So we're altering the values that are in the array. Then we're going to return 0. So then x gets the value 0, which came from double array, but the array itself still remains as it should be. Is that what you're looking for, Sean?
Yeah, yeah. I was just mainly concerned with whether or not void was a requirement for editing an array.
So these functions here, double array and input array, only have what are called side effects. So you got parameters coming in, but it's not itself returning anything. All it does is it alters memory that's outside of the scope of this function, and so it's changing something else somewhere in the program, and that's called a side effect. Anything that goes into the function and comes straight out of the function are the arguments or parameters and the return type, but anything that happens outside of the function, any memory or variables that it alters that are outside of the function are called side effects. So since these functions only have side effects, they can be declared to be void. If they actually did want to return a value, like let's say double array's job was not only to double the array, but maybe sum them up along the way, then we could return that as a value from the function. So it would have a side effect and it would return a value. All right, so as I said, I think we have enough information now to be able to look at some of the programs. How many of you have run into this before?
Yeah, I've had to change my password probably 5 times in the past couple weeks, it seems like.
There was a way to do this so that, is that it? No, that's not it. Nope. Ah. All over the place now. This looks promising. Except I don't know my password because it's one of those random passwords that my password manager keeps, and I'm on a totally different website now. Oh, we're going to have to go back to the beginning. Is that down here? Nah, we're back on this one. Okay, I'll do it this way. This one knows my password. And you always, whenever the browser offers to save your password after logging in, where you go like, it knows my password, I just typed it in. What's happening there is the authentication system receives your username and password, and then because it's a third-party authentication system, right? It's not part of Canvas, and it's not part of, I mean, it's part of Sierra College, but it's not part of Canvas. So what Canvas does is it sends the username and password over to the authentication system, and the authentication system checks your username and password, but it doesn't send like your username and password back to Canvas. What it sends back is basically a one-time random string of characters that stands in for your password. And so when it sends that back, your browser goes, oh, it looks like you just changed your password. Do you want me to save that? And you should always say no, because then it will save that one-time little random string, and then your password won't work from that point forward, which leads you to change your password again. So, and I always click on like, no thanks, I don't ever want to do this again, but it prompts me every time, and it's kind of annoying. Okay, so I believe we can do warm-ups 3.0 and 3.1. We can't do level 3 yet because we haven't learned about strings. Now, there is a page here called Just Enough About Strings, which will teach you probably what you need to know about strings to be able to complete the level up assignment, but let's just talk about the warm-ups right now. And then on, on Monday, we'll talk about strings. So this warm-up is really easy. You're just going to fill in an array with some numbers. So elements numbered 0 through 9 are just going to get the values 0 through 9. Elements number 10 through 19 should get the values 100, 110, 120, up to 190. Try to do both of these with loops. So, I mean, you could put in 20 assignment statements and, you know, it would work, but try to do it with loops instead. And then elements 20 to 25 just get the values 4, 8, 15, 16, 23, and 42. There's no rhyme or reason behind those. So just assign them directly. And then finally, elements 26 through 39 will be the first 14 values in the collats sequence starting with 7. So you're also going to need that collats function from last week to be able to do this assignment. And then finally, before your program exits, finish with a loop that prints out the entire contents of the array. So that's all it is. You're just filling in various sections of the array with either loops or just direct assignment statements. And then another warm-up function is called copy array, and I've given you some template code. So you can copy this right off the web page. And there's two ways to run this program. If you change this define right here to 1, it will fill in your array with random values. If you leave it at 0, it'll just fill it in with some predetermined values. And the idea is to create 2 new arrays, one called pos for positive and one called neg for negative, and then copy the values out of the source array into either the positive or the negative array. If it's greater than 0, copy it into positive. If it's less than 0, copy it into negative. And if it is 0, don't copy it. So the first thing your program needs to do is iterate through this source array and basically count up how many positives and how many negatives there are. And then once you've got that, you can then create the 2 arrays you need using those values as the size of the array, and then copy the values into one or the other. I've written most of the program for you. So you'll need to write a piece of code that counts up how many positives and negatives there are. And then you need to write the code to create the arrays. And then finally, you need to finish up the program here. So it prints out not only the positive array, but also the negative array. So that should be fairly straightforward to do as well. You shouldn't basically need to touch anything kind of above this line right here. So everything above this line has to do with filling it in either with random values or predetermined values. Shouldn't need to touch any of that. All your code goes below this line right here. If you do get stuck, I've got a couple of hints where you can drag and drop these tiles into the correct order to kind of get an idea about how to count how many positive or negative numbers there are. And then also some help about how to copy an array. Okay, so again, 2 short warm-up programs, not too complicated. And then you can take a look at that string program if you want to dive into working with strings. But basically the idea there is you're going to capitalize the words in a sentence. So the first letters of each word are going to get capitalized. So there's a couple of tricks there, like how do you determine, not tricks, but a couple of things you have to worry about there, which is how do you determine if a letter is at the start of a word, and then how do you capitalize it, taking into consideration that it may already be capitalized, or the word, or the quote-unquote word, might actually be a number, so you don't want to capitalize that. Maybe the word starts with punctuation, so you don't want to capitalize that. So there's a couple of little things there to kind of keep track of.
Now, we can get started on that, but did
Oh.
you say that the associated lectures would be next week?
Yeah.
Okay.
Because Monday was a holiday, we kind of missed a day.
Right.
Or you can go back through my YouTube channel and find the corresponding lecture from last semester. It would have been dated, I think, February 8th or February 6th, somewhere in there. I can always guess at the dates because the way our school calendar works, they start the semesters always on like the same days of the month, except that because the length of a year is 52 weeks and 1 day, the dates are always skewed by 1, right? So September 7th today, which means the corresponding day last semester would have been February 6th. Kai has posted a link to, I guess that was last semester's video. All right. So, what remaining questions do you have?
Nobody else had a question. I had something that relates to compiling, but
Okay.
not necessarily to the lecture.
Okay.
When we import a statement, say stdio.h, for instance, does it import the entire, I don't know, that entire library and compile it along, or does it only import what we need for our program to function?
That is a great question. It has a nuanced answer. So the only thing that's in that file is just function prototypes and things like constants. So there's no actual code. There's no actual like loops or variables in there. So there's nothing in that file that results in your program getting bigger, because there's no actual code in there. There's no actual instructions. So that the actual code for those functions exists in the standard C library, which is already on the system, already compiled for you, already ready to go. So the answer is no.
Okay.
There's no extra code that goes into your program. But yes, it does run through that entire file and at least take a look at every single line. Now, the compiler has a final stage that I didn't show you in the phases, but it's got one final stage called optimization. And that's where it takes a look at your compiled program and then tries to make it run as fast as possible or be as small as possible. You can pass in some options to kind of change its behavior. One of the things it'll probably do is it might run through your program and look to see like, oh, you've got a function here called blah, but you never call it anywhere. You have it written, but you don't call it, you don't use it anywhere. So I'm going to throw it away. And So that's one thing that might happen is if you link in some libraries, but then you end up not using all the functions in that library, it might end up just tossing out the stuff that you don't need and making your program a little bit smaller. That's the case for like libraries that you wrote yourself and you compiled yourself and are linking yourself. Now the standard libraries like the math library and the C library, though, like I said, already exist in the system and they can't be changed. So what happens there is the file itself, when you're trying to figure out how to tell this story without confusing too many things. Remember, at the very last stage, I said the linker's job is to take your program and link in the standard C library and the standard math library and then make the final executable. That was kind of a lie. Conceptually, that's correct. And you can actually make an executable that is the combination of your program and the standard C library and the math library, and you'll get this gigantic executable that's like 2 or 3 megabytes, even for like hello, because it contains the entire contents of the C library, which contains networking code and memory management code and code for working with files, and even if you're not using any of that stuff, it still gets linked in. And the math library contains all the code for doing the math functions, even if you only use 1 or 2 of them. So you get this huge executable. And that uses like lots of disk space. If every single executable you generated was this ginormous thing, you'd quickly chew up available disk space, because you kind of got to combine it with all the other people that are doing the same thing. So to save on disk space, what the operating system does when you link it together is it doesn't actually pull in those libraries. It just like puts a reference to it and says like, hey, when you run this program, it's going to include the C library and the math library. So there's a compile time linker and there's a runtime linker, which is called the loader. And what the loader does is it loads your program to memory and then it looks through that table of contents and it goes, oh, I see here that you were also linking in the standard C library and the math library. I'll bring those in right now. And so the linking phase is actually broken up into 2 phases. There's the compile time linking, and then there's the runtime linking. And so in this case, the runtime linking just brings in the standard C library and hooks it into your program, and the math library and hooks it into your program. And so your program doesn't use more space on disk because there's just a note there that says, link it into the C library and link it into the math library when you run it. So that has a couple of benefits there. One is it means that all the programs that are running on the computer at the same time are sharing that one copy of the C library and of the math library. So you don't have 200 individual copies of that library sitting around taking up memory. You've got only one copy, and since it's read-only code, you don't need to make any more than one copy of it. And all the running programs just point to that one copy in memory. So it saves time there, and also it ensures that when you run your program, you're always running the latest version. Right? If we do an update on the system and a new version of the C library gets installed, the next time you run your program, you'll pick up that new version with some bug fixed, hopefully. If it was linked in at compile time, then you'd have to recompile your program in order to get the latest version. Now, it could be that you want to run the older version. Maybe some bug was fixed, but also a new bug was introduced, and you really want that old version. And so then you could do what's called a static link at the compile time to make sure that you always linked in the old version and not the new version, or link in the version you wanted versus the one that's the most current one. So that was like a long answer to your question, which is, does it compile in the whole C library? No, it doesn't, because it's already been compiled for you, and it gets linked in not at compile time actually, but at runtime. And the only thing that's in those header files are just function prototypes and constants and type definitions, which themselves don't actually make your code any bigger. They're just notes for the compiler to say, hey, there's a function called printf. The code is not here, but there is a function called printf. And so just that information itself doesn't result in executable instructions for your program. It just results in a note to the compiler that there will be a function called printf. Same thing for the math library. So did that answer your question, or did it complicate things more?
It answered my question. Yeah, you were scrolling through, I believe, the math.h declarations of
Uh-huh.
in a previous lecture, and I was just like, wow, that is a lot of information, and only the square root functions are relevant to a program. And I see this, I've looked at the size of the a.out file compared to the source code, and it's always larger by well, in the couple that I've looked, larger by like a factor of 3 or 4. So
When you link in the math library?
no, just the executable compared to the source code is always
Oh. Yeah, because it contains all these other
larger.
these little notes, right? I mean, there's sort of a minimum size to an executable because, I mean, there's the main that you wrote, but, and most people will tell you that main is the first function that gets called, but that's also a lie.
Yeah.
There's actually a couple of functions before that that get called and are always the same because there needs to be a function whose job it is to kind of like initialize the memory to receive the rest of the program, you know, to kind of like set up standard input and standard output and standard error, the 3 files that are open all the time, and also to allocate memory for the stack and allocate memory for the heap. So that's kind of like some housekeeping that has to be done before your program can even run. And so there's these other functions that have to run first. And those also get linked in at the link time, is those initial little housekeeping functions. And so that can cause your executable to be always at least a minimum size because of those housekeeping functions. Does that make sense? There?
It does. Yeah.
So your main may actually just be a very small portion of that executable. There's this other stuff that also has to get compiled in to your program in order for it to run. So main is not actually the first one that gets run. It's called something else. And then that one calls main. There are ways that you can, I mean, these are just tricks that some programmers do, is you can take an executable and then you can go through the actual code and rip out the stuff that's absolutely not necessary. Some of the stuff is just boilerplate. It just sticks it in there because 99% of programs need it. But the 1% that doesn't need it could actually remove that stuff. And so you could write a program that does away with everything that's not necessary and get something pretty small. But, you know, at what savings, right? You know, it went from 3 kilobytes to 1, but it still uses the same amount of space on disk because blocks are 4 kilobytes.
Sure. Yeah. No, I was one of the questions that spawned from this whole thought process is, well, space is not a constraint necessarily anymore. But back in the day, did people have to get in there and tear out function declarations they didn't need and stuff?
For the most part, the compiler handles that for you.
Yeah.
You know, you can turn on the optimizer and then it'll rip out stuff that isn't needed, and it will actually make your code really small. It can do things like take the body of a function and just inline it right into your code. Like take out the fact that you're calling a function entirely. That'll make your program run faster, a little bit faster, just a wee bit faster, and make it a little bit smaller. That's when you're working on a microcontroller, sometimes you'll turn on the optimizer and you'll optimize for space rather than speed. Because your microcontroller might only have 8 kilobytes of memory and, you know, maybe a couple kilobytes of actual program storage space. So you really want to make the code as tight as possible, and you're willing to give up a little bit of time for that. So we'll be able to talk more about the optimizer. I think the optimizer is like a fascinating stage that, you know, like I said, it didn't show you on the diagram, but what the optimizer can do is just amazing. Like C has been around so long that a lot of research and development has gone into making that optimizer be as good as possible. And some of the things it does to your code to make it run faster is mind-boggling. And keep in mind, the optimizer was written by people. Like a programmer sat down and said, basically, if I see this pattern in someone's code, I'm going to do this to it to make it run faster. Like, just to give you a little insight here, let's say you have a loop that counts from 1 to 100. and it sums up that number, or maybe it counts from 1 to X, right? And it keeps a running total of that sum as it's going. So if you count from 1 to 10, you'll get a sum of like 45, I think is the answer, or 55. And if you count from 1 to 100, you get a sum of 5,050, right? And so somebody wrote a little piece of the optimizer that says, if you see a loop that looks like this, where it's counting from 1 to some number, and it's keeping a running total as it goes, pull that code out and just replace it with the actual number. Wait, what did it say? So if I wrote a loop that counts from 1 to 10 and calculates the sum of that number, it will rip that code, it'll rip that loop out and replace it with the number 55. That loop will just cease to exist, and it will just say like sum equals 55. If I wrote a program that counts from 1 to 100 and it sums up the numbers, it'll pull that loop out and replace it with sum equals 5,050. It won't even do the calculation at all. It just knows what the answer is. And then if I write a loop that goes from 1 to X and I sum it up, it'll replace it with the what do you call that? The sum formula, right? Was it the beginning number times the ending number divided by 2 or something like that? It just replaces that whole loop with just like a calculation. And that's one of the things the optimizer does is find common places, common like things that you do in your program that could be sped up tremendously by just pulling that code out and replacing with something different.
Good thing the code is 50 years old, because that sounds like it would need about 50 years of work to account for all of the things you might see.
Yeah, because a lot of that is like some programmer went, huh, I'll bet I could speed up this code if I just did this to it. And then they write that little pattern matcher for the optimizer, and then everyone benefits from that. So we'll get a chance to see more about what the optimizer does in a few weeks. I have some like example programs where this is your code, and then we'll look at the generated code and go, wow, that looks like completely different. But it's faster. All right. Someone, Andre on YouTube, pointed out that Apple is doing their presentation right now, so everyone needs to click over to that and learn about the new iPhone that's coming out. I personally am more interested in the new Macs, but that's supposedly coming in October. I finally just picked up one of the new MacBooks. Finally picked up one of the new MacBook Pros. Finally got around to that. It's fast. I mean, my old one was 7 years old. So this is nice and fast. This is the new one that you're seeing on the screen. I mean, it looks pretty much the same on the screen, but it's a whole lot faster. Now I'm
like, with the Apple Silicon?
Yeah.
Yeah.
And now I am like, after playing with this, going, oh, I should upgrade my desktop too, because that one's also 7 years old.
The Mac Studio is nice.
Yeah. And I was watching some videos, and they were saying like, should you get a Studio? And they said like, for most people, if you want, you know, your own screen, you want your, you know, because Apple's offering right now is you can get an iMac with a 24-inch screen, and they used to have 21 and 27 as their two offerings, but now it's just 24. And I'm like, 21's a little small, but 24 is not quite big enough. I like the 27 because I have a 27 on my desktop right now. So the only way to get a 27, and this is what Apple does, right, is they make computers that are almost but not quite good enough, so you have to go to the next step up to get what you really wanted, and then, but that's too much. So they intentionally leave gaps in their product line. They don't fill in those gaps because a lot of people want what's in that gap. And so you either have to go with what was below or what's above. Apple knows a lot of people want this, but they offer you this and they'll offer you this.
Yeah, I am shopping Surface Studio laptops right now, and I see the same thing. There's a gap where the thing I want isn't there.
Yeah, that's marketing at work there. So I watched Rene Ritchie, and he said, you know, most people would be satisfied with just a Mac Mini. It'll do lightweight video editing, which is what I'm starting to do now. It'll do, I mean, and of course the older machines would do video editing too, but the new Apple Silicon processors can do that, like without any stutters, without any glitches or spinning beach balls. So I said, most people will just get a Mac Mini, but you don't get the base model. You should go up to 16 gigabytes of memory. You should add a little more storage space to it. And so I priced it out, and I said, well, that's $1,000 now, not $600 for something closer to what I want. The Studio is only like $800 more than that. And it comes with a way faster processor, and it comes with twice as much memory, and for just like a little bit more. So why don't I just get that? And then get that nice 27-inch display that they've got. So that's what I'm like, should I just get the Mini and trick it out, or should I get the baseline Studio, which is going to be like 4 times better for just a few hundred more? So that's where I am right now. Oh, first world problems, right? Anyway, so I think that's about it for today. I hope you got something out of that discussion about arrays, and we'll be back on Monday, and we'll continue our discussion with arrays, and we'll also talk about strings, which are really just character arrays, but kind of special ones. And then you'll be able to complete all the assignments for this module. And then after arrays, what are we doing after arrays?
More arrays?
More arrays. Is it literally called more arrays? It is called more arrays. I surprise myself at some of the really creative names I give to these modules.
It's like naming variables. It's just...
So that one there is really kind of, yeah, I'm going to show you some common array algorithms, like how to sort, how to search, how to reverse an array, to switch it end for end. And then you'll be able to program a game called the reverse game, which uses array manipulation to put some numbers in order. And then if there's time also, I can show you image processing. So since an image is basically just an array of pixels, we can do stuff with images, like we can darken them, brighten them, we can flip an image over, we can flip it end for end. You could even maybe do like 90-degree rotations on it. So kind of the stuff that you take for granted in Photoshop or just about any other image manipulation program, someone's got to write those programs. And so get an idea about how those work. So that should be about it. Any other questions? Someone just asked, can we have access to the function video? And I presume you're talking about the one from last semester. And so just look on my YouTube channel. You'll have to click through to videos and then scroll all the way down to get to about February 5th or so. Or maybe you're talking about, last week's. Oh, that should be on there. Oh, no, sorry. Last week's, I was gone last week. So we did not do the YouTube streams last week. So what you'll have to do is, again, find the corresponding videos from last semester. So that'll be like January 31st, February 2nd, somewhere in there. And it'll be pretty much the same content. Okay. Well, have a good weekend, everybody.
All right.
Thank you.
Yeah.
And you too.
Take care. Bye-bye.
Recording.
Yeah, was it Blazo? Yeah, so look through my YouTube channel, and I think I have it over here. Let's see. Oh, no, you don't want to see that one. You want to see, nope, you want to see that one. You want to see, what am I looking for here? This is my view of it. You want to see your view of it. Library. Is that it? There we go. We'll go to videos. Actually, you can go to playlists. And then I have C programming from, if you just do C programming right here, then here's a list of all of my stuff going way back. Doesn't have the dates on them. Here we go. Here's the ones you're probably looking for. So functions, header files, more about functions, header files. So these are the videos. Oh, you don't see what I'm looking at. Sorry. All the sonnets and the plays and everything Shakespeare wrote. So all right, so I went to my YouTube channel, and then I found the playlist for C programming right here. And then scroll through, and around video number 20, 21, 22 is where you're looking at for the stuff that would have been presented last week. Oh my gosh, that is a younger, thinner me from about, how long ago was that? 10 years? Yeah, so the information about compiling and linking stage is in those videos. One of those two. All right, well, I am ready to go get some lunch. It's about 12 o'clock here. So I hope you all have a great weekend, and I will be back on Monday. So have a great day. Take care. Be safe. I'll talk to you later. Bye-bye.